Let me introduce my next speaker. It's Nick McKeown. He's Kleiner, Perkins, Mayfield, Sequoia Capital Professor of Computer Science and Electrical Engineering at Stanford University. He's also a faculty director of the Open Networking Research Center. Nick received his Bachelor of Engineering from University of Leeds and Master of Science and PhD degree from the University of California, Berkeley. He also worked for Hewlett-Packard Labs. He helped architect Cisco's CSR 12,000 router. He was a founder of several successful startups. He co-founded the Open Networking Foundation and the Open Networking Lab. He was recipient of numerous prestigious awards. And I have to say that for many years I was teaching a course on telecommunication switching systems, and of course scheduling algorithms proposed by Nick played a very important role. So Nick, the floor is yours.
Raise your hand if you've heard of this thing called software-defined networking. Right? There's been a whole load of hype over the last 10 or 15 years. And I bet you with 1,000 people in the room, if I asked you all for a definition of SDN, I get 1,000 different answers, right? So I'm going to start by giving a little bit of a retrospective. I'm going to make a claim that even if I hadn't existed, even if my student Martin Casado hadn't existed, even if the reporter who coined the term software-defined networking had never been born, actually we'd be talking about the same thing because it was kind of inevitable. It was an inevitable consequence of the desire to disaggregate, to reduce cost, to have more control over the way that networks operate. You may already know that. It's not really a deep technical observation. It's really more of a business observation. So SDN is primarily a business change. I'm going to start by talking about SDN Act 1, which is a retrospective, or rather a change which is ongoing. And in Act 1, network owners take charge of their control plane. What this really means is that those who own and operate networks have started to take control of how their networks behave. If there's an Act 1, there must be an Act 2. I'll give you a little sneak preview. Act 2 is where they take over control of how the packets are processed as well, and that is happening through something called programmable forwarding planes. It seems innocuous. It seems as though we're going down and rather than going up. But in going down, we're going to actually get more control, and that is a change that's just beginning to happen now. But let me start with Act 1. So you may have seen one of these things before, a big supercomputer or a big mainframe computer. These were very common in the 1980s, and at that time, they were built out of proprietary hardware, proprietary operating systems, with lots of applications on top. Actually, not many applications, because if you wanted an application, you had to buy it from IBM. What happened in the 1980s was the rise of the microprocessor. And as we know, this changed everything. But let's think about why that was. It allowed other companies to build computers apart from IBM. It meant that with microprocessors of several different flavors, with well-defined open interfaces, instruction sets, you could build operating systems on top. We're all familiar with at least 3 that are very commonly used today, and there are many hundreds more that have since gone by the wayside. So with those 3 that are prevalent, it created, let's face it, a Cambrian explosion of applications on top. A small computer industry turned into a gigantic computer industry, and that was even before the smartphone came along and took it even further. The networking industry has been a bit slower in making this transition. In the case of the networking industry, big mainframe routers used to consist of proprietary hardware, proprietary operating systems, and proprietary features that sat on top. Disaggregation in this industry came as a consequence of merchant switching silicon that started in the mid-2000s, really getting a toehold, primarily because of companies like Broadcom and Mellanox and Marvell. And although those interfaces are not yet quite open, they are at least well-defined through APIs and SDKs. Those open interfaces allow for control planes, and there's been a lot of interest in developing control planes, switch operating systems, network-wide operating systems, cloud management software, etc. and then a huge number of applications on top in which network owners and operators customize their network in order to meet their own specific needs. A lot of this effort has gone into the development of the control plane. So if you look at the papers, the open source code that's been developed, the proprietary products that have been created, they're mostly in this middle layer. And this is because a lot of the complexity that we think of in networking sits at this point. We had to get this right first before the applications and customization and features really could take hold. This has now largely taken place. And so over the next decade, you'd expect to see much more widespread customization of how networks are built. But to return to my earlier point, I want to make the claim that SDN was actually inevitable. And it was inevitable because the rise of Linux meant there was a stable code base that gave people the confidence to produce open source that could run in the infrastructure. The rise of Whitebox servers in data centers gave people the confidence to build their own equipment by buying the chips, wrapping sheet metal around it, adding a power supply, and sticking it in their infrastructure. And the third was the rise of merchant switching silicon that gave people the ability to build those systems and add the Linux and add their own software on top. Just to prove to push the point home a little bit, legacy servers inside data centers 15 years ago looked like this. They were from companies like Compaq and Dell and HP. They consisted of CPUs, operating systems, applications. They were soon replaced by Whitebox servers, and in fact, every big data center in the world now use Whitebox servers. They're still using x86 CPUs with Linux running on top, but applications that they write for themselves. The same is happening in network switches, in data centers, and throughout networking. What was once legacy equipment built by OEM equipment vendors out of CPUs plus a switching ASIC, OSs and applications, has now been replaced by white boxes. This one happens to be blue, just because it was built by Facebook. An x86 CPU, a switching ASIC, a merchant switching silicon ASIC, Linux, and then control program written on top. Why are they doing this? One obvious reason is cost. Let's have a look at an example big data center that would be built today. We have about 500,000 servers, about 25,000 switches. Generally speaking, the ratio between servers and switches is about 20 to 1. Just think for a moment, 25,000 switches in one data center represents actually a significant fraction of the entire switch market in just one place. That's bigger than the entire number of switches in big telco networks. And that's just inside one data center. I'll return to that in a minute. What they noticed about 15 years ago was these switches cost $10,000 to $20,000 each if they went to a merchant or an OEM equipment vendor. So that meant that the network switches would cost about $250 million for one data center. They could instead buy merchant switching silicon, wrap it in sheet metal, add Linux, add their own protocols on top, and they could build them for, at most, $2,000. Some people will argue it's more like $1,000. So imagine you're building 5 data centers per year. You're saving $1 billion by building them yourselves. You can hire a whole team to build the switches, write all of the software, which, of course, at the big data center companies, they have armies of people who can do that. And you can still come out ahead and save a lot of money. So this is why they started doing this in the mid-2000s. And every big data center company in the US and in China now builds their own networking switches. But if you ask them why they did it, they'll say this was actually the secondary reason. The biggest reason was for control. As soon as I write the software for my network and put myself in control, I can centralize the control where it's easier to manage. If I've got a homogeneous network under my control, much easier if I can control it centrally. You centralize if you can. You only distribute the control if you can't. And this has become the mantra of many of the mega-scale data center companies. Once they've centralized the control, they can customize and they can differentiate their network so that Google's network can be different from Amazon's, can be different from Facebook's, can be different from Alibaba's. And so therefore, they can compete for our business by providing a better network. Or they can use it to further reduce the cost. One of the biggest applications that has been reported that the big data center companies have used writing their own software to improve is the way in which they route traffic over their networks, what's usually called traffic engineering. They have noted on multiple times that instead of using standardized one-size-fits-all protocols for doing this, if they write it themselves, they can increase the utilization of their networks from below 50% to approximately 95%. So if you imagine they spend billions of dollars per year on running those networks, on operating those networks, they can further halve the cost of so doing. So in fact, pretty much all networking equipment is disaggregating today. The rise of merchant silicon across the industry for residential access, for 5G, means that all of this equipment is gradually being disaggregated. Base stations, 5G gateways, optical and metro transport networks, Wi-Fi access points, residential broadband access, even enterprise networking equipment, switches, routers, firewalls. And there's a saying that goes around that software is eating the world, of networking too. It's hard to find widely published metrics of this change, but one place that you can look is in the open source community. So let's look at the way that open source code and software for networking has evolved over the last few years. Let's first of all look at Linux, which was really what started it all back in the mid-90s. Linux really took off when commercial companies such as IBM, Compaq, and Dell, and then Google started to adopt and use Linux very widely. And so by about 5 years ago, the majority of smartphone servers, websites, mainframes, and supercomputers in the world were all based on some variant of Linux or Unix. What changed things for networking was, around 2000, was the rise of good enough merchant switching silicon. It meant that megascale data center companies, the first one was Google, could build switches from switch chips plus Linux in the mid-2000s. And then after that, commercial switches like NEC and HP added OpenFlow interfaces to allow them to be remotely controlled. Open vSwitch, or OVS, as a hypervisor switch became adopted by Linux as the way to interconnect packets between VMs. And then after that, the takeoff was just very, very fast. By 2012, the number of virtual Ethernet ports for connecting VMs was larger than the number of physical ports in the world. And that ratio is probably 3 or 4 to 1 by now. Over time, more open source has been created, both for the switch operating systems, for the way that the network is managed, for the way that it's virtualized. And so today, I'm sure I've missed many off this list, there is an acceleration of the amount of open source that's being created. One way to think of this is a sign of industry that's maturing. Those who wanted to grab a proprietary advantage have grabbed that advantage, and now open source is coming in to commoditize that portion of the industry. So it would seem that now I can tailor my network, tailor the software that I own to do all sorts of things. And in fact, if you are a network owner or operator today, it would seem that you can write the software yourself, you can buy it from somebody else, you can download it off the internet and customize it for your needs, or you can commission someone else to write it for you. And in fact, most network operators take this for granted now. And so you see these big efforts like AT&T's Domain 2.0, all of the big data center companies, Verizon, Telefonica, British Telecom, China Mobile, all moving in this direction of taking control of the network by taking control of the software that controls it. So I can quickly deploy new protocols, surely. I can monitor precisely what my forwarding plane is doing. I can fold expensive middle box functions like load balancing, firewalls, gateways into the network for free just to make them part of the routing infrastructure. I can try out my beautiful new ideas. Now I own my own intellectual property of the ideas that I put into my network. I don't have to share them with others. I can differentiate and make mine better than my competitors, and I can own my intellectual property. Is that true? It all seems to make sense, right? But I'm actually going to tell you there's a bit of a crock in the middle of this. Because if you think about what a network does, networks are based on packet switching. And packet switches, they transfer packets from one place to another. That's all they do. All the network is a means to transfer a packet from one place to another. It doesn't do anything else. All the rest is just software. If you can't change the way in which the packets are processed in your network, then I would argue you're not really in control. If you really want to be in control of the network, you have to change the way that the packets are processed. Everything I had on the last slide, you can't do unless you can change the behavior of the packets. So that's why there is another change that's taking place now, which is move that control down into the forwarding plane. Let me try and explain. This is the generic icon for a switch or router. Let's take a look inside. There's a switch operating system. There's a bunch of protocols that run as applications on top of that switch operating system, and a driver and a switch chip. There's a CPU in there that's running the switch OS that I'm not showing. That switch chip at the bottom is a pipeline of stages which processes different portions of the headers. Every switch chip is built this way if it's to be high performance. And the state of the art today is switch chips that can process several terabits per second of data at the same time. So incoming packets are processed by that fixed function pipeline. And the argument goes that in order to make it very fast and efficient and low cost and low power, it needs to be fixed function because you couldn't possibly make it programmable. Now imagine that you want to add a new feature. In fact, imagine it's 2010. In 2010, Cisco and VMware got together and they defined a new protocol for distinguishing traffic between tenants in a virtualized data center, and that tagging protocol was called VXLAN. You probably all heard of VXLAN. If you look at how VXLAN works, it takes about 2 pages to describe it. It's really simple. It's just a way of saying this packet belongs to this tenant. To write the code to populate the tables would take any of you about 2 weeks, max. And so when they wanted to change and add this capability of VXLAN into switches and routers, the first thing they had to do was to add the software. The second thing they had to do was to change the pipeline. And you can imagine what that took. So in order to be able to change the pipeline so that that little yellow header that I've added can be processed for those VXLAN packets, instead of taking 2 weeks, it took 4 years. In fact, it was 4.5 years before the first silicon actually showed up that had this feature. This isn't a niche application. This is in the most profitable, the most highly invested portion of networking today, and it took 4.5 years to bring out a simple new feature. So what's going on here? The thing that seems to be going on is that those who own networks, they want a new behavior. They go huddle at the IETF and they figure out together how it is that they're going to deploy it. No one wants to make the investment until they're sure it's a standard. So they go off to their software teams and they say, can you do this for me? And they say, sure, it'll take us a few weeks, maybe a few months. They go off to the ASIC team and say, can you add this feature? And they say, sure, I'll just wait 3 or 4 years and then we'll have it for you. And so that's the long pole in the tent, and not surprising that it takes a long time to deploy new capabilities into the architecture. And so I would argue that this is probably the main reason why, when you look at it, the internet architecture is essentially the same as it was when I was an undergraduate, and that's a long time ago. Is it because they got it perfectly right the first time? Of course they didn't. There is no area of IT where we got it right first time. It's because it's really, really hard to change. Now that the control plane software has been made more flexible, it really feels like time to make the forwarding plane more flexible. Because today, if you have a new feature, the equipment vendor who sold you the equipment, they can't just send you a software upgrade to change the way that packets are processed. New forwarding features take years to develop. By then, you've figured out a kludge to work around it. You've overloaded one mechanism with another. Just think how traceroute works. It's a mess. Why is it that networks operate today off a kludge that was force-fit into something it wasn't supposed to do? That's how we debug our networks. It's shocking. Your network gets more complicated because you start doing unnatural acts. It gets more brittle. In other words, it becomes less reliable. And eventually, when the upgrade is available, it either no longer solves the problem you had 4 years ago, or you need a very expensive forklift upgrade to replace all of the hardware. So essentially, networking systems today are built bottom-up. The switching chip that defines its behavior for reasons of efficiency, power, and cost has dictated through a data sheet written in ambiguous English what it is that it will do. It tells us upwards how we are going to operate our network. What it means is the biggest data centers, the biggest networks in the world, their networking behavior is determined by a chip designer. And this isn't very likely to work very well because most chip designers have never operated a big network in their lives and very unlikely to know how to do it. Surely, just like every other part of IT, it should be that those who own and operate the infrastructure should decide for themselves how it should behave, because they are the ones who know how to do it. The thing that's held us back is this conventional wisdom in network that I have been guilty of propagating too, and that is that programmable switches are 10 to 100 times slower than fixed function switches. So it leads us to a natural Act 2, in which network system developers, people who build networking equipment, take charge of their forwarding plane too. What this essentially means is describing in a high-level language the behavior that you want to take place, and then compiling it and downloading it to operate in the infrastructure. As soon as you see it this way, it seems kind of obvious, but that conventional wisdom has stood in our way. So it's happening, and it's happening now. And I'm going to describe a little bit about how it's happening and how people are using it. But first of all, I want to explain why it's happening now. In fact, it's a kind of a logical consequence of what's happening elsewhere. And this is the development of domain-specific processors. If you look at the most recent computer architecture book from Patterson and Hennessy, you'll see a lot devoted to domain-specific processors. That's because nowadays there's a lot of effort put on processor design for specific types of accelerated domain application. We're all familiar with the original processor. This isn't a domain-specific processor. This is a general-purpose processor. What we did, we wrote in a high-level language. We compile it down to run on a CPU. What makes that possible is a well-defined instruction set, a compiler that knows what it's doing, and a high-level language which is independent of how the processor works. The same thing happened in graphics. I can remember when graphics was done on big cards of fixed-function logic. Nowadays, you write in a high-level language, you compile it, you run it on a GPU. The same thing happened in signal processors. I'm old enough to remember in DSP classes in graduate school when people were arguing about whether there would be a time when people would no longer build fixed-function DSP pipelines. Could it ever be the case that you could build high-performance DSP engines for which you could write in a high-level language, compile down to run on a machine that was domain-specific, targeted at doing fast operations, even though it didn't know what MATLAB was? The same thing has happened more recently in machine learning with the TPU. You write in TensorFlow or another high-level language, it gets compiled down to run on a machine that is optimized for that application. And the strange thing is that that hasn't happened in networking. Yes, there were things called network processors, but that was kind of cheating. They were just CPUs thrown down on a core. So over the last 7 or 8 years, working with a group of people at different universities, at different companies, starting with people at TI, and then working with a number of people at companies like Intel and Google and Microsoft, we gather together a group of people who say, it's really about time to design pipelines and to design a language that will bring to networking what has happened to these other domains. You may have heard of this thing called the P4 language. The P4 language is a language for describing forwarding behavior at a high level. It gets compiled down to run on a PISA architecture. This one isn't leaning, hopefully it's straight. The PISA architecture stands for Protocol Independent Switch Architecture. It's an architecture that is unaware of the protocols and features that you've described. It's just a means, a uniform means of taking the program after it has been compiled. Let me explain what I mean. In the PISA architecture, it's a pipeline of identical match action stages. Now, I should say for a moment, what I'm describing here is the equivalent of those pictures that you learned about RISC when you were first learning about computer architecture. In other words, this isn't how an individual chip may be built, but it's a rough architectural description. It's a cartoon view that helps us understand its primary features. So, for example, I show 4 identical stages here. A real implementation might have 3, it might have 30, it might have 300. That depends on the particular implementation. The important thing is they're all the same, and they're all capable of doing matches. That's what the blue rectangles are. And then ALU operations, that's what the little trapezoids are, on the packet headers as they go through. In order to be able to process packets in a generic way under programmatic control, first of all, you need to be able to parse them, decide and recognize the different headers, be able to rip them apart, and then stick them into this pipeline in order for them to be processed. Let me show you this through a little animation. Here is the packet arriving on the left-hand side with a variety of different headers. What the parser, the programmable parser that we've told what to do, is going to rip out the headers and stick. You can think of them as sticking them on a big bus or typing them, however you like to think about it, and then presenting them for individual matching. There may be multiple matches that we can do in parallel because they have no serial dependencies. And it turns out that most packet processing has no serial dependencies, so we can do this. Because generally layers are added for orthogonality, and so therefore they tend to be able to be processed in parallel. Those headers will then go through that match and then an action that will modify them. You could think of it as mapping it to a different value, adding a header, removing a header. Just think of it as a geometric mapping as it goes through that stage. Now, there are some serial dependencies, so we would typically go through multiples of these stages as that packet goes down that pipeline, and eventually it's going to be put back together again with its data and then sent on its way. So that's the generic way of thinking about this piezo architecture. That pipeline knows nothing about protocols. It has an instruction set, but it doesn't know what MPLS is, it doesn't know what IP is. It's just a generic forwarding engine designed to be very, very fast. Now, you express the behavior in P4. I'm not going to go through this. It's a language that looks a little bit like C, but it's a way of expressing the headers, the match action tables that you want, and then the processing that you would like to take place. If you want to learn more about the P4 language, I'd encourage you to look at p4.org. It's an open source consortium of about 100 different organizations, companies, universities, researchers, who have been using it as a means to modify the behavior of forwarding engines. Now, this wouldn't be very interesting unless there was a target, and I'm not here to promote a particular target, but I want to mention one that I personally have been involved in, but there are many others, and there will be many others over time. This is just an existence case, and the reason I'm mentioning this is you would think that there was still that 10 to 100 times performance penalty. That may have been true at large scale when the dimensions were large for transistors. At around 16 nanometers, for reason I don't have time to go into today, the difference between fixed function and programmable goes away. In short, it's because the logic is such a tiny fraction of the chip that it disappears under the wires. And so the difference between fixed and programmable has gone away, and it has gone forever. What that means is, regardless of this particular chip, it means that in the next 10 years, you will start to see every switching device become programmable. Because if you can have fixed or you can have programmable, and they have the same power, performance, and cost, you will always take the programmable. So it means everybody will do this. There's nothing magic here. The interesting thing, because of the pipeline, this PISA pipeline, it means that any program that compiles and runs will always run at line rate. So you don't have to worry about funny corner cases of things running slower. They have the same power and the same cost as the fixed function. So let's look at how it's being used. I'm going to go through 3 different kinds of usage. The first one might surprise you, and that is one of the most common things that I've seen people want to do as I've gone around talking to various companies, data centers, researchers, government agencies about the things that they want to do. Almost always in a commercial environment, they say, how do I throw stuff out of my network? Amazon reports that about 30% of the failures in its infrastructure is from networking. Others have reported that of those failures, the majority take place because of protocols that they didn't even know they were running. It's features that were in fixed function devices that were there and operating, for which they had no local expertise, and so it would take them hours to go and solve it, when if they had actually got rid of it, it would have never happened in the first place. So this would be an example of what someone might do. A group of people in this p4.org open source community got together, people who had built a large number of switching chips and switches, routers, firewalls in the past, and they coded in this P4 language all of the forwarding behaviors, production quality forwarding behaviors that they could think of, about 45, 50 of them. It's an open source program that anyone can download and execute. And these would represent all the things that you want. I don't know of a single network that actually needs all of these things, so what most people do is they comment a whole load of them out. So if you've got a program that describes the behavior that you could have, and you don't want those behavior, then it's common sense that you just comment them out, and then you compile, and then they're not there. You don't have to worry about them coming to bite you. And so you would then put that through a compiler from my own personal switch.p4, And then I would compile it, and then I would run it on that programmable device. Of course, once I've reduced the feature set, it means that all of the resources, all of the tables, all of the bandwidth, all of the processing capability of that device is now devoted to the small number of protocols that I want. And so instead of having a whole load of tables for, I don't know, 7 layers of MPLS that I don't want in my network, suddenly I just can liberate all of those and use them for IPv4, which everybody has in their network. The second thing that people do is they add new features. They add private features that are to differentiate, things that they want that other people don't have in their networks. And you'd be surprised at how much this happens. First of all, though, to calibrate this, get an idea of protocol complexity and how that has evolved over the last 20 years. This is what a protocol graph looked like in a switching chip of about 15, 20 years ago. Basically, you had to decide whether it was an IPv4 packet or an IPX packet. That was really all you had to do. Now, you're not going to be able to see this very clearly. This is a partial portion of that flow graph for the insides of a switching chip that would be programmed with that switch.p4 program. Let's zoom in on a little bit of it, and you can see it's very, very complicated. What people do, though, once they can actually modify it for themselves, they will add new encapsulations and tunnels. That's kind of boring, but that's what they do, in order to be able to identify packets in new ways. They'll tag packets for special treatment. They will try new approaches to routing. Big data centers are actually moving much more towards source routing, so they can simplify the forwarding tables. This is something they can do once they can program the behavior. They try out new ways for congestion control that involve switches and an indication of the congestion that actually comes from the switch, something they've not been able to do before. Or they do fancy things like processing packets further into the packet, like processing ticker symbols at high speed for high-frequency trading. But there are kind of boring examples. What I've been surprised by is the things that people do that I hadn't thought of. And this is what makes programmability interesting. It isn't what the chip designer can do, it's what the programmer can do. Because Cambrian explosions in programming take place when you enable a whole new army of programmers. And they have ideas that I would never think of. Here are 3 simple ones that I thought were kind of cool. The first one, yeah, kind of interesting. Taking a layer 4 load balancer. Typically, hundreds of servers are devoted inside data centers for just load balancing traffic as it comes in. Well, why don't you just fold that into the switching chip and just change that P4 program that you've written? There are deployments in China now that are doing that, where they liberate huge numbers of servers in order to be able to program to add layer 4 load balancing as essentially routing in their network. Fast stateless firewalls, the ability to do audit trails on firewalls by being able to do thousands of updates to the forwarding rules, and then being able to do it under your control rather than having to go through an expensive piece of equipment. An interesting one that I saw recently is something called netcache, which is taking large key value stores like memcache and being able to put a cache in front of it that sits in the network that can decrease the time for the tail latency for doing lookups into large memcache servers by about 95%. The last example that I want to give is network telemetry. And this is the thing which is driving probably this change most quickly. I mentioned traceroute earlier, and I'm going to take a swipe at the way that we debug networks just for a moment, and then describe how that's in the process of changing. Imagine that you have a network that looks like this today. It has packets that flow through it. Here are those packets. And think that you have to debug that networking as part of your job, that network as part of your job to keep it working. So it would be natural to take a packet and ask it, which path did that packet take? What was the path that this particular packet took through the network? I mean, I'd like to be able to say that this packet visited this switch at this time, this switch at this time, this switch at this time. Isn't it funny that there's not a single network in the world today that can answer this question? Now, imagine that you want to ask not only how did it get there, but why did it get there? That would be a natural thing to ask, right? If you want to do security or reliability or figuring out why a packet is in the wrong place. In other words, which rules did it match? The switches know. The switches know that it visited them and at what time they visited them. It knows the rules that they matched on. All of that state is inside the switch. So wouldn't it be good if the packet would actually tell me I visited this switch and then I followed this particular rule? Why can't it do that? There isn't a single network in the world that can do that. It's not surprising that we still rely on traceroute and ping and things like this to operate big networks. If we're interested in the performance, I might want to know, how long did my packet queue in a switch? Why can't it tell me that I was delayed by a certain amount? There isn't a single network in the world that can tell you this. That red number there indicates a problem. I would like to be able to go to the switch and say, tell me the time series of the occupancy of the packets in that queue. There isn't a single network in the world that can do that for you today. Who did my packet share a queue with? In other words, whose fault was it that I encountered that big congestion? There's not a single network that can do that. All these 4 questions, these basic questions, don't allow us to say, what is the breakdown of the occupancy in that queue? I'm the green one. I'm not the problem. Who is this orange one, this aggressor flow that is causing all this congestion in my network? So it's kind of funny, actually, that we try and operate networks without these basic questions, all of which is known to the switch. All of that information is known to the switch. If you could answer these ground truth questions, I would argue that you could debug networks much faster than you do today. So all of these could potentially be done with a device that's programmable, because the person that operates the networks, these are the first things that we would add. And that's, in fact, what's happening. I've observed people doing this over the last few years. This is something called inbound network telemetry, but there are many, many other ways that you could do this, in which you simply tag the information that the switch already has into the packets as they go past. You add this cumulatively to the packets through the network. And then when it gets to the other end, you rip off that information before you've put the packet to the end host. It's a kind of a natural thing to do. So, in summary, programmability is being used really for 3 things: reducing complexity, adding new features, and this network telemetry is the first driving factor. What it tells us is, SDN, and I would argue that this is kind of the natural follow-on conclusion of SDN. It's really about who is in charge. It's about changing who is in charge of the behavior of our networks. Network owners and operators have already taken charge of how their networks are controlled. They're now in the process of deciding how packets are processed in their network as well. This will take a long time. The network industry has a lot of vested interests, and they're very entrenched. And so this will take another 10 or 15 years to play out. The chip technology is there already, and that's just as a consequence of 16 nanometer and below. As a consequence, we'll see this prevalent everywhere in all types of switches that are used for networking. The big thing, the thing that excites me most, is the new ideas that will come from it. Beautiful new ideas, now owned by the programmer, not the chip designer. And that is where the innovation will come from. Thank you.
Well, thank you so much for the nice talk. The first question is that, what is the future of solution link SAND, server network assisted dash, that provide communication between application and network to optimize the data transition?
If I understand the question correctly, it's once you have more programmatic control at all layers of the network, then you have a foundation that you can begin to correct, verify, formally verify, trust. It means that you have more trust in your ability to then modify its behavior in service of applications. So people often refer to autonomous control of networks or self-driving networks. You get the illusion. A lot of that is to do with once you've got a stronger formally verified foundation, applications can start to influence the behavior of the network, either to make it more reliable or just to do better stuff for it. And so I think this is an inevitable consequence of this change.
Well, the next question is that it has been almost a decade that the programmable networks are in discussion. Why we cannot see it in a deployment? Why the network admins don't have any answer for that?
The term programmable network, I think, has been used in a variety of different contexts. So if the question really means software-defined networks, they really started in about 2008 when Google started to build their own networks in this fashion. They were the first. Now, all 4 of the main data center companies in the US all define the software for their networks. All of the 4 in China do the same. And now nearly all of the telcos are starting to do the same thing. So this is a change that is already well underway. What hasn't happened is that the network in my building at Stanford is still built the old way. And that's a much harder nut to crack. And that will take a little bit longer before that becomes lower cost, more control of the local network administrator. Give it 10 years.
Well, after data centers, where do you think SDNs are most likely to be adopted?
Yeah, so it's definitely true that data centers have been the first place that SDN has been adopted. And that's largely to do with cost reduction and because the data center owners have armies of programmers that have allowed them to develop the software that they needed. But the natural next place is in the big telco operators, the AT&T, Verizons, China Mobiles, Telefonicas of the world. They obviously operate big networks as their business, as their primary source of business. In the past, they were well placed to be able to develop the software and the technology for themselves. But over time, as they've depended more and more on the network equipment providers, this has been harder for them to do because they've largely laid off or no longer nurtured and developed large armies of software developers. And so it's been a little bit of a tricky transition. They've watched as the hyperscale data center companies have taken on SDN with a vengeance. And in the last few years, you can see that they're trying to organize, trying to train, trying to hire large numbers of software developers in order to be able to make this transition for themselves. So they're the ones that we can expect to see happen next. If you look at the work of the Open Networking Foundation and the ONOS distributed operating system and CORD, you will see large deployments starting to take place around the world in telco networks, and I expect that to happen more and more over time. So they will rely heavily on open source in order to bootstrap that development, and then they will supplement and customize that with their own software developers over time. Now, the big business in telcos is in wireless, because this is the biggest growth area. So cellular networks have a particular challenge because they've been really hemmed in by very draconian protocol requirements, by standardization requirements, and a lot of intellectual property. So it's been much harder to disaggregate the cellular equipment. What we're seeing, though, with 5G is much more of a move towards like data networking with much lighter weight behavior in the forwarding plane. And so those equipment are now being disaggregated next. And so we can expect to see that happen a lot over the next 5 years. Some of the biggest development that I've seen in SDN in the last few years has been for cellular infrastructure. And so I think that we'll see that rolled out over the next few years.
Thank you so much.
Thank you.